markets like there's no tomorrow.
Hello everyone, welcome after the break. Today we will continue with the second block of the financial engineering course of lecture number 9. Our focus today will be about more advanced hybrid models. In this lecture, this block, we'll be focusing on the stochastic volatility hybrid models, in particular Schoebel-Hull-White and also Heston-Hull-White. Here I will show you the impact of different correlation coefficients on a hybrid payoff. In this case, we'll be talking about a basket which consists of a stock and also of a bond. And then we will investigate impact of different correlation coefficients on this payoff evaluation. The main part here will be about Monte Carlo simulation, so how to perform efficient simulation of those hybrid models, especially if we talk about simulation with stochastic volatility. And the most important model, the Heston-Hull-White model, will be discussed in some detail. We will finish today's lecture with a summary, and I will give you a number of homework assignments. Enjoy! As discussed, extension of the Black-Scholes model of stochastic interest rates does not really help in generation of implied volatility skew or smile for the stock. What we can further do, we can extend the Black-Scholes model and not only introduce stochastic interest rates, we can also introduce very simple normally distributed process for the volatility. So this is what we are going to do right now. We consider the so-called Schoebel-Hull-White model. So this is a model which consists of these two processes. So this is DST, ST. It looks like just the Black-Scholes, except that the interest rate and volatility are both normally distributed. So you can see that for the interest rate part, we have a Hull-White model that we already discussed before. For volatility, we are using Onsten-Umbeck. So this is a process where the mean reversion, the long-term mean of the process is fixed at sigma bar. So this is another hybrid, of course. In this case, we also assume a full matrix of correlation. So those Brownian motions are correlated. So this is, say, a very straightforward extension of the Black-Scholes Hull-White model with the stochastic volatility. And that's the name of the model is Schoebel-Hull-White. So this is the title. So Schoebel is the part where we have only a process for ds and d sigma, and Hull-White is the process for the interest rates. Unfortunately, as you will see, this very simple and very intuitive extension, let's say this is the simplest extension you can think of, it is not so simple if we would like to solve this problem, solve this model in order to derive option pricing. So the problem here is that maybe there is not such a big problem that we assume volatilities to be normally distributed, because that's sometimes a complaint here, because if you look at this volatility, it can be negative too. Right? So we have the case where we have volatilities that can be negative. However, the variance is still of course, positive because we're looking at a square. But anyway, if this process here would be also positive, then you see that we are always multiplying with a Brownian motion that can also flip the sign. So this is not a really big issue. However, the structure of the model, as you will see, has some limitation with respect to the affinity. This means that this, let's say, very intuitive extension of the model of the Black-Scholes-Hull-White with stochastic volatility by inclusion of the normal distributed process, it's not so easy. So, for example, if we consider Hull-White model, Heston model with the Hull-White model, or this Heston model, that volatility structure there, it will be much nicer to deal with. And this will be very clearly shown in coming slides. And let's start with this model. So we have this Schoebel-Hull-White full matrix of correlations. There is, of course, a relation between the parameters. So this model, in a special case, can also be represented as the Heston model. The big limitation of this model is that, as you can see here, that we can link Heston model with the Schoebel-Hull. So maybe you remember in the course of computational finance, for every parameter that we had in a Heston model, we could easily find out what is the interpretation and the meaning of each of the parameters. So for example, there was the mean reversion, there was impact on a skew or smile, there was a level of volatilities, there was a gamma vol parameter for the curvature, and skew parameter, the correlation. And so that was very nice and transparent, because essentially by looking at the implied volatility shape, you could find out, you could already have a feeling what is the parameter setting you should think of in order to calibrate the model. However, here, if we look at those parameters, so gamma is easy, because gamma, we see it's just twice, Heston gamma is equal to twice gamma of Schobel-Zu. But volatility, long-term mean, for example, you see it is related. So long-term mean for Heston would be related by a volatility curvature and also mean reversion. And here is also easy. So this kind of rather nested, complicated, convoluted dependence between the parameters in order to get this clear impact, clear relation to the Heston, that you will see also in a numerical experiment. It's a limitation. So from this perspective, if we look at this kind of relation between the parameters, you will see that Schobel-Zu model has less flexibility in the calibration of the model to the real market than Heston model. And this comes from the fact that this volatility structure here is not rich enough. So this means that not all the shapes of implied volatility, skew and smiles, can be achieved as they can be achieved, for example, using the Heston model. And of course, this has to do with the fact that in a Heston model, once we have a failure condition not satisfied, we can have this fat tails in a variance, in a volatility process. And here, obviously, we don't have we have a very nice Gaussian process for volatility. This obviously means there is a less limit, there is more limitations, less flexibility in getting sometimes very sharp skews and smiles. This is also the model will collapse to Black-Scholes if we choose volatilities to zero, or some parameters to be killing the volatility. By killing the volatilities, of course, and also for interest rates, this model will collapse to time-dependent Black-Scholes. So the problem is that, of course, if we have if we just look here in this dynamics and we look at the affinity features, of course, in the drift side, this is always easy. Everything is nicely defined. But if we look at the squares and all the products of the volatility parts of the Brownian motions, you see that the first term already is quadratic. And actually, Schobel-Zu model belongs to the quadratic affine models, quadratic models, where this doesn't belong directly to the affine class processes. And how we can solve this problem, actually, if we see that this product squared, this will be sigma squared dt, we can tackle this problem by introducing another variable, variable v, which would be defined as sigma squared t. And so we have, let's say, we introduce additional process that will be handling this sigma squared. And by this extension, our system of stochastic differential equations becomes extended. We have one more process for dvt, and this dvt, of course, is a sigma squared t. If we apply Ito to this equation, then we end up with this process. And you see that at this point, our system, so dx and also dv, very much so, if I look at this process and also this process, you see this pair resembles very much the Heston type of stochastic differential equation. So we still have this volatility, which is square root of v. Here is 2 times gamma, square root of v. And here the complexity part, where we have this additional dependence on sigma t. Sigma t is driven by another process. It is this normal process. So you see that actually this limitation of the flexibility that I just mentioned is related to this convolution here in the drift, that we have this extra dependence on additional process. And this is not anymore this relation between sigma and v in here. This is a really big constraint on flexibility for getting implied volatility smiles and skews. Let's say the range of the smiles and skews is much more limited as for the Heston model. And of course, we have these additional processes. We have this R and sigma. I did here a little bit of decomposition. This is something that we already have seen for the Hull-White model, but this is just engineering. Sometimes this helps you to derive the characteristic function because you can decompose this dependence on theta t function. But except for that, we have those four processes. So we have extended space. And what happens that if we have this extra process introduced for sigma squared, this model becomes finite. So now if we look at the instantaneous covariance matrix, this is how it looks like. So we have a VT, we have a sigmas. So everywhere where we had the sigma squared, so we had a sigma squared t, then essentially this is VT. And then here we have a sigma t, a VT, and so on. So everything is linear, but in the terms of state variables. But now this set of state variables is extended with extra dimension of this sigma squared t, which is equal to VT. So it's a quadratic class of processes. And because of this, we are able to find the characteristic function. Unfortunately, because of this limitation in terms of this extra process, the set of Riccati equations that we need to find to establish the characteristic functions, it's much more involved because this relation here also with sigma and v, this makes it this set of Riccati equations much more complicated compared to the Heston model. And unfortunately, you cannot, one of these equations, which is there, this ODE, the complex valued ODE, you cannot solve analytically. You have to do it numerically. This is also means there's some additional cost involved because for every Fourier argument u, we have to find, we have to integrate over time. And that can be expensive because this means that if we have a 300 cosinus expansion terms, this means we have to calculate 300 integrals in order to get the characteristic function. So this is another limitation of the Schobel-Zoo model. This extension on the Hull-White doesn't really affect that. This complexity would be there even with exclusion of this process from the system. I didn't show you the solutions for this process because it's rather involved. You can look in a book. We provided that solutions and those ODEs. However, we will discuss in this block, of course, the numerical results. So those are the shapes of implied volatilities, smiles and skews, depending on the parameters we have chosen. So we have here, for example, impact of gamma. In a Heston model, this volatility parameter was just implying the affecting the curvature. Here we see that gamma affects also level. So there is an impact on the curvature, some impact on the curvature in this parameter, but it's more level. If we look at kappa, the same. We have essentially impacting level, not so much impact on the skew. Then if we look at the correlation is similar as we had for Heston model. There's a kind of a rotation of the implied volatility smile or skew. So this is kind of okay. And then sigma bar, again, level. So you see in a Schobel-Zoo model, although we have additional parameters, they are not really adding so much to the dynamics, to the flexibility of smiles and skews, because most of the parameters, mainly they impact the level. And this is because of this convoluted relation between the parameters if we compare the model to model of Heston, except for maybe the correlation. This would also imply that in calibration, you could keep some of these parameters fixed, because there's no point of calibrating 3 parameters if all of them, they have rather the same impact on the implied volatility, smile or skew. Now let's take a look at the Python code. Here I have implemented the Schobel-Zoo implementation for the characteristic function. So if we go here, this is characteristic function Schobel-Zoo-White, and this is part which is here. So we see that we need to find those functions for the characteristic functions VD, VE, VA, and each of them, they are computed here above. There you see that there's a plenty of equations that need to be incorporated, and moreover, we have to perform numerical integration. I think this is for A. So for every argument you see of U, we have to perform numerical integration. Here I'm doing actually 2 times trapezoid integration. So this means that if we have 10,000 expansion terms for the cost method, we have to perform 10,000 integrations. Of course, this is rather expensive. And especially if you think of calibration, where we have to evaluate the model many, many times in order to find optimal parameters such that the model fits to the implied volatilities in the market, this becomes very, very expensive. However, in the book, we have discussed the calibration, and also there are codes available so you can easily download them and play with them and see how this correlation, sorry, the calibration, how it performs compared to the Heston model. So I have chosen here a set of parameters. In this experiment, we will be changing one by one of these parameters and looking at the impact of implied volatilities. Here, again, we evaluate everything with the cost method, which is adjusted for stochastic interest rates. It's very much like what the regular cost method was, except that we have to handle with this zero coupon bond that we take outside of the expectation. And then here we look at the implied volatility for the black 76. So if I run, you see that it takes some time because it's every single call, every single set of parameters, we have to perform many of these integrations. I have chosen here, maybe this is also 2000 expansion terms for the cost method. So obviously that's not being very cheap. And this is also not really optimal, but I just want to illustrate the results. So those are results, exactly the ones that we have seen in the slides. So you can play with this function and see what is how you can improve it. Of course, I see there is a lot of room for improvement. This code, it is more a brute force implementation I have performed just for the purpose of illustration to show how to deal with those models. Since we are talking about the hybrid stochastic differential equations and the purpose of simulating scenarios to evaluate our XVA or VAR calculations for a portfolio of consisting of products from multiple asset classes, it is also maybe a good idea to take a look at a classical, a very simple hybrid payoff. So payoff in which our performance or our payoff will depend on two different asset classes. So I have prepared here so-called diversification product. So if we look here, we see that our payoff will depend on a stock at time ST, and also we have a zero coupon bond, so the performance of a zero coupon bond. So how you can think that if we have, this is a time grid here, we have our maturity of our option time t, and then we have some time horizon t1, and we are obviously at time t0. What we are going to do, we are going to look at the performance. So at the expire date of our option, we'll be looking at the ratio of a ST. So here will be ST over ST0. And then so we will have a performance of our stock. So the level doesn't really matter here. And on the other hand, we'll be looking also at the performance of a zero coupon bond. So at this point, we'll be looking at a bond over this period of time. So it'll be P, T, T1. Obviously, this bond will be known at this point. The same stock will be known at this point in time. And we divide by the value of a bond at time today, T1. So you see, we are always looking at the initial values, and we both instruments, we scale by dividing of today's value, which is present, which is seen at today date. This payoff is a European type. So of course, although we are using kind of a hybrid payoff, which depends on two asset classes, the nature of the payoff, it is European. Of course, here we look forward, we look in the future, but actually it's not the case because this zero coupon bond, PTT1, it's known at time t. So there's nothing stochastic at time t because this value will be known. Because we can simply, at time t, we can read this value from the market or from a yield curve that is built at that date. And here what we have this omega weighting function, which is just a weight from our portfolio can be we can balance our portfolio. We can be 100% in the performance of a stock or 100% of the performance of a bond, and of course we can have everything in between. So you see that this is very straightforward hybrid, and of course this variance, because what the main driver of this payoff, maybe not main, but one of the contributing drivers will be the correlation between this performance and this performance. because those two are quantities are correlated. And of course, for ST, it is easy to see because ST at time t will be S t0, and then we have this E, and then we have integral of our RT dt minus, and of course, maybe I should include this volatility here, so minus 2 sigma squared t dt plus we have also integral over sigma dt dwt. And for the PTT, of course, here we also have affinity, so we know that T1 will be given in a fine form because we are assuming we are dealing with the full white model. This will be A plus B times R at time T. And actually not T1, but T. This A and B will be depending on time T1 and T. So you see, there is a variance of this sum of these performances will also depend on the correlation of sigma and actually the volatility of this the volatility process, but also stock itself. So this Brownian motion here. So you see there is a kind of combination of all the factors. So here we have dependence on volatilities from interest rates, volatilities from stocks, and also we have correlation between those Brownian motions. So you see there is a kind of nice interplay between those two asset classes. And so in this way we can diversify, of course, assuming some correlations between these two asset classes. So if we look here, I've prepared some experiment. So we are looking here at the value, the price of our derivative, depending on a weighting function. And here we evaluated this for 3 different correlations. So we have a correlations between a stock, Brownian motions of stock and interest rates. So interest rates, we have a 0 correlation, minus 70% correlation, and 70% correlation. And then you can see that depending on the weighting function, a weighting factor, this impact on the price can be rather significant. But also note that this weighting, it is not really 0-1, because weight can be also, we may have more stocks or more bonds in the portfolio, in our, let's say, our payoff. And here we're looking for this is the relative correlation effect. So this will be a price, and here we are looking in terms of basis points, how many basis points impact. So this is essentially a little bit a re-representation of this picture into this. Let's take a look at the code. The code is very straightforward because in order to illustrate this impact, this effect of correlations, I have just implemented Schobel-Zoo model. So we have a Schobel-Zoo full-white model, and the implementation is performed using simple Euler discretization. So there's no fancy discretizations, much more advanced discretizations for hybrid models we will discuss today in today's lecture. But here, this is more about illustrating that when pricing of hybrid payoffs, correlations play important role. And as you can imagine, sum of 2 random variables, if we have correlation between them, the variance of the sum, it is not the sum of variances, so that difference would have a contribution to the value of a payoff. So what we do here, we have a range of parameters. Actually, those parameters here, you see, those are recalibrated parameters. Actually, no, those are the, yes. So I have done, those parameters are taken from the book, and for each of the correlations that we have chosen, the model has been recalibrated to the market data. What you can also do, you can fix the parameters, for example, sigma bar, gamma, etc., and you can only change the correlation and see the impact. Obviously, if you have correlation chosen, let's say from the historical data, naturally what we could do is to recalibrate your model to European options, because obviously the correlation that you have chosen will also indirectly have impact on pricing of calibration to Europeans. So normally you would start with calibration of the correlations to historical data, keep those correlations fixed, and then you calibrate the remaining of the model parameters to the market data. Otherwise, you may have a mismatch. So you may change the correlation, but actually the impact that you see on your diversification product would come because you have essentially mispriced European options. So this is important to keep in mind. Let me run it, and this is basically the very simple code. So the results should be in a second. So this is the same what we have just seen in the graph. I think there's nothing to be mentioned regarding this code. Today we will discuss more advanced discretizations. If you like to learn more about different type of discretizations, I recommend to revisit the course of computational finance, where we concentrated on different discretization schemes and also the impact of a number of time steps on the convergence results. Since the Heston-Hull-White model is a very limited model in terms of flexibility to calibration of generation of different implied volatility smiles and skews, let's take a model which actually has those, let's say, flexible features and see whether we can extend this model with stochastic interest rates. Namely, we take right now the Heston model and extend it with a full-white short rate model for interest rates. So I think everyone is familiar now with the Heston model. So it's a stochastic volatility model with the variance process given by the square root process. And so this is defined here. We have those two processes. And then we extend this framework of stochastic interest rates with the Hull-White model. Of course, we know that the Heston model under the log transformation belongs to the class of affine jump diffusion processes, so there is not a problem there. Let's see whether we are able to extend the model with extra dimension and whether the model still belongs to this class. This is what is illustrated here. So actually, again, as in the Schobel-Zoo case, drift part is nicely affine. Typically, the problem is with instantaneous covariance metrics when we look at all the squares and all the combinations. So of course, this part, it is a pure Heston model, so it's fine. And however, if we multiply this term by this term, we see that we will have a eta, a correlation between those two Brownian motions, and we end up with a square root of v. And this is illustrated here. So we can easily see that this model is not linear in terms of state variables. Of course, what we can do now, or at least what we can try, is to introduce a variable, the same as we have done for the Schobel-Zoo. We can, for example, say we have a new variable psi, which will be equal to the square root of vt, and then we apply ethos, lemma, and see the dynamics. Unfortunately, this approach is not successful because the dynamics of dvt, it is not, first of all, it is not fully correct to derive this dynamics because a process of vt may attain 0. So this means that we cannot really apply directly ethos lemma. However, if we don't even follow that procedure, you will see that constraint that not all the conditions to apply ethos lemma are satisfied. Even if we would just find this dynamics, we will see that this drift and volatility terms for this process xi, they are very involved, and they involved non-linear terms. And actually, if you derive this dynamics, you will see even in the drift, we will find, so if we look at the d psi t, even in the drift, we will have terms like 1 over square root of vt. So obviously, these terms, those type of terms are not linear, and we cannot easily fix it to make this model affine. So this, let's say, attempt that we could do for the Schobel-Zoo model with extra variable to extend space variables, this is not really applicable in the terms of the Heston-Hull-White model. So what we can do, we have to go towards approximations. So how to approximate those covariance terms such that actually we can find these characteristic functions. Keep in mind that here, this model would be affine if we would assume some correlations to be 0. So if we assume correlation between interest rates and x, so this correlation between these two to 0 and also variance and r to 0, then that would not be a problem. Of course, the correlation between the variance and interest rates is rather unclear what that means. Typically, this correlation between these two Brownian motions could be estimated based on the calibration to Europeans, but typically this will not have significant impact. So let's say this correlation we can set to 0. So that term will be 0, that's fine. So then one problem is less, we solved. However, we still have this problem here where we have this correlation between stock and interest rates. And this one actually, to some extent, we can observe in the market, or at least from the historical data, when we look at the short-term interest rates and stock. So there could be correlation. And historically, these correlations are not strong, but could vary from minus 60% to 60%, depending, of course, on the economical circumstances and the market overall. So this correlation, we cannot choose a zero. And actually, if we would even choose the zero, what's the point of having this hybrid? This means that we have a hybrid which is not a hybrid, and that's basically limitation in that case, because the model would just simplify to essentially a Heston model with stochastic interest rates which are non-correlated. So the benefits of having hybrid model and also, let's say, pricing of a hybrid, let's say, diversification product that we just discussed, this will have no impact because there will be no correlation. So we need to keep this correlation because that's the whole purpose. And for given correlation here, we need to evaluate characteristic function to calibrate this model to the market data. So we need to find this characteristic function such that we can evaluate European options. We can do some approximations here. Of course, that will be the first. There's only one way to approximate this quantity. What is also important to stress is that if we price European type of option, then a correlation between interest rate and stock, and also this volatility part here, those are not the main drivers of option pricing. So if you think about it, volatility of a stock will be mainly driven by the the option price of stock will be mainly driven by the volatility of the stock and the variance. So basically, this is the crucial part which determines the value of European option or exotic event options on a stock. Those elements, so those higher order terms, those are having less importance. Those are higher order terms. Those are less importance for evaluations. So this means that I feel comfortable with introduction of some approximations. I would not feel comfortable if we do approximations already at this level, because then this error would propagate. But here we are looking at the correlation between the stock and interest rates. So here maybe we can do something, and at the end we can measure the impact of this approximation when we compare European option prices from the Monte Carlo simulation and from COS Fourier transformation. So those two at the end, by comparing, we can assess the impact. Okay, so the first and very straightforward approach that is typically used for these entries is to map the square root of a variance process on its expectation. So we map it on the first. There are also possibilities to map it, this quantity, on a stochastic variable, which is then defined to be as an additional variable in the space variables. So then we can define a new process, but not necessarily as an ethos, the derivative of the square root, but we can define a new process which is belongs to defined processes, and then we can map moments of the square root of v on that process. So there are two different routes. Here I would like to present only the first one because that's the most straightforward. The other one is a little bit more advanced. Of course, if we have this mapping, we need to find the expectation of the square root of Vt, and this is also known in a semi-closed form. So we have an infinite sum, some gamma functions, and we have some functions c, kappa, and those functions will be actually given on this slide. So this is, let's say, as you can see, this expression is it's easy to implement. However, it's not super cheap to evaluate because those gamma functions and also infinite summations, those are not nice things to have. Of course, this sum will converge to some at some point. So if you have implemented this approximation for this expectation for the square root of variance, you have to keep track when the sum converges enough, when it's close enough, when it stabilizes, and then you can truncate this summation. Of course, this summation, also this number of terms that are relevant, will depend on a configuration model parameters that you have used in your simulation. So this is kind of a little of the problematic part, but it's also from the engineering perspective, it's nice to implement, and also nice to make it sure that this whole analysis of checking where the truncation takes place, it's a quite pleasant and easy thing to do. So if we have this, so if we have expectation, also we can calculate the variance of this VT. This variance will be important later on because we will be doing also some other approximations of this expectation. So here the limitation is that this expectation may be a little bit computationally expensive if you like to calculate at every point every time t, and we have to do it for many summation terms. And since this involves some gamma functions, this is not very cheap. So the next step would be to simplify this expression and to find some analytical closed form formula that performs as good as this infinite summation. So this is the variance. So it is, you see, it's rather straightforward. Extension is basically almost the same formula, except that we have some squares. In the book, we provide more details on those derivations. So here I just give you the final result. If you are interested in details how to arrive those formula, then I recommend to revisit the book. Okay, so the approximation that I would like to discuss here is so-called delta method, where we approximate some function g of a variable x by using the Taylor expansion around its expectation. So if you have a variable x and you have a function of this variable x, you can expand this quantity around the expectation of that function of the variable. So you see we have a g of x and we have a g of expectation of x, and then we have this stochastic part, and then we evaluate derivative of function g of x at expectation of x. So, of course, this is given the assumption that we have a sufficiently smooth function, and if two moments of this function g exist, then we can do that. And this is also related to why we need to calculate variance and the expectation. So, since the variance of a function gx, so this is now we are going to link it to this delta method to what we have derived in previous slides. So since the variance of gx can be approximated by the variance of the right-hand side, so on the left-hand side and right-hand side here, this is the variance what we arrive as an approximation of function gx. So here you see that we have a variance. We have all those terms on the right-hand side here, which is basically equal to the square of a derivative of x evaluated at the expectation of x, and then we have times variance of x. So those two terms we can combine together and arrive at the approximation for this expectation of the square root of variance t. So if we now substitute for function g, we substitute with square root of vt. This is expression what we have. So we have a variance of square root of vt is approximated by this term. On the other hand, by definition of a variance, this is the expression of. If we now substitute, we equal these two equations. This is the formula we arrive. So you see that we arrive at the expectation of a square root of vt is approximated by square root of expectation of vt, and now we have a function which depends only on the expectation of v, which is nicely given in closed form, and also variance of vt. So those two expectations, and actually this one too, they don't depend on those complicated gamma functions. Those are closed form because we are dealing with a variance process, which is a CIR process, and for those expectation and variance is an elegant and given in a nice closed form. So you see, this is another approximation. Of course, there is some limitation here, because for the sum sets of parameters, the term under the square root may become negative. So then we provide also some conditions at which parameter sets this approximation performs sufficiently good, and when you have to go for this exact. So you can basically think like this. For sets of parameters, when the square root is, the term under the square root is positive, you can evaluate this easily. If you have a square root term under the square root is negative, then you can evaluate using the exact, more expensive infinite summation term. And here is also a further simplification what we can do. So here actually we substitute. So because of the variance, I mentioned that for the process VT, we have it's a CIR type. So this is the exact solution for the variance of the Heston model. We have expectation given in closed form, variance in closed form. Then our final result is basically given in this term. So we have essentially, you see those, we just substituted the expectations and the variance from the CIR to this nice closed form solution. So of course, now if we have this expectation of the square root of Vt, we can simply substitute that to the instantaneous covariance matrix. So we can map this term on the expectation of the square root of Vt, and that would allow us to evaluate this characteristic function analytically. What is also important to keep in mind that this expression will be time-dependent function. So we map it actually not on a one value, but we map it as a time-dependent function. Because still we have those terms will be it will be integrated over time. So then we actually dealing with time-dependent function of a square root of Vt. At this point, I'm not going to introduce the Monte Carlo simulation and then simulation of it of the cost method. Those will take place later when I will show you how to perform almost exact simulation of the Heston-Hull-White model, or in generic case, hybrid models in high dimensions. And after that, we will compare the Heston-Hull-White model as given in this approximation setting against Monte Carlo brute force and almost exact simulation. So to be nice, three models simulated, Euler discretization, brute force, almost exact simulation for Monte Carlo, and also we will have here the Fourier transformation using those approximations. And then we can quantify the error that we make using those approximations. In this lecture, we have already discussed three different hybrid models: Black-Scholes-Hull-White, Schobel-Zu-Hull-White, and Heston-Hull-White. Now it's good to take a look at the Monte Carlo simulation, whether it's Euler or Milstein. Let's see how this extension of a standard Euler discretization for a single, let's say, Black-Scholes model, how it would look like if we have additional dimensions and also the complexity related to correlations. After this, let's say, introductory part about discretizations, we will move to the almost exact simulation, in particular of the Heston-Hull-White model. And after that, we will combine those models and we will perform one analysis, one numerical experiment, where we will see whether approximations we have developed previously, whether they are good and how bad if they are bad. So let's start with the discretizations. This is generic system of stochastic differential equations where we have a stochastic volatility process for the stock, and we have some process for interest rates. Here you see we are rather generic because we allow the function bx, bv, and br to be specified. It doesn't really matter what form, so this means this also would apply to Schobel-Zu model, and also not only Hull-White, but we can also think of CIR and some other short rate models. Of course, if you like to keep this model framework to be affine, then we have to really take care of the cross terms of the covariance matrix and of course of the drift terms. Our objective actually is to concentrate on the processes we have already discussed, so Schobel-Zu and Heston model. So if we define the discretization, so in Euler discretization, also Milstein discretization, first, maybe if you would like to learn more about those convergence of the different discretization schemes, I recommend to revisit the course of Computational Finance, where I discuss in detail how those convergences look like, what are the differences between different discretizations, how to control the error, how to improve your simulation, and so on. But here we are concentrating now on the Euler discretization. So you see we have an iteration step. So the Euler discretization is the simplest discretization, where we have an iterative step where essentially we approximate the integral of the whole interval between times ti and ti plus 1 by freezing the values or evaluating value only at the initial point of that integral. So this is what happens here. Of course, here we have performed also the logarithmic transformation. So here we have S. First step, in order also to improve your convergence, is good to perform logarithmic transformation. As you know, normal distribution, if we would like to sample from normal distribution, we can get better results than if the convergence is much faster compared to log normal distribution. This is why if we know something about the process, it's good to take this information outside. In this case, we know that this is kind of exponential form, so we can perform logarithmic transform, and that would facilitate the convergence improvement. So here we do it for the first part, for the first process, we have evaluation of Ri. So you see that this is the process for interest rates, half of the volatility term squared, and then we have three here noises, Zx, Zv, Zr. Those are the correlated Brownian motions. Actually, here it's not Brownian motions because we have removed also the time coefficient outside. So those are just, this is maybe not correct here, what it says, they are not correct, they are not Brownian motions. Those are just 0 ones, normally distributed 0 ones. I will correct that in the slides too. And of course, depending on functions for Bx and Bv and Br, we will also encounter some issues. Maybe you remember in a simulation of the Heston model, there's a problem that CIR process, if the failure condition is not satisfied, there is a probability that 0 is attainable by the volatility paths. So if you look at the variance process, it may start here, it will hit 0 and bounce back, and basically this is kind of pattern you can expect for the variance under the CIR model with the failure condition which is not satisfied. And of course, if we perform Euler discretization, and then this condition of hitting 0 and bouncing back is not really satisfied, so there is a positive probability that the variance at the next step, this probability that Vti plus 1 is smaller than 0 is bigger than 0. So this is essentially the issue that we have with Euler discretization if we deal with processes like CIR, especially if we have a failure condition which is not satisfied. However, there are fixes, and also in the course of computational finance, I have discussed those fixes. Here we will just mention that in the next part, we will discuss almost exact simulation. So those, let's say, brute force fixes are not really necessary in the implementation. However, I will show you how to do that. Next step is that if we have hybrid models, I think I already have mentioned that the correlation between the variance and interest rates is something that is not really clear how to estimate that correlation. And if you would like to use this parameter as a free parameter in order to calibrate the model to European options, the impact of that will be very, very limited. So there is no essentially need to have that parameter, especially if it simplifies our derivations and also facilitates better results in simulation. And actually, this is the case. So if we can have volatility or the variance process to be independent of as many processes as possible, that's typically very beneficial, because if we deal with Cholesky decomposition for the correlations, and we know that, let's say, exact simulation for the variance process, and we know that from the Heston model, then we don't want to have any, let's say, extra terms which are coming from dependence with interest rates. Because if this dynamics for Vt would be different than CIR, for example, then we may not be able to use anymore the explicit solution exact simulation from the CIR process. So if possible, always keep those variances as independent of other processes as possible. Of course, the correlation between the variance and X, this is the one that we know how to deal with, and then you don't need to make it equal to 0. However, the correlation between those two, I feel kind of comfortable with setting up to 0. And of course, later you can perform experiments to see this impact, and you will see that it's very marginal. And also the interpretation of this parameter, it is rather unclear. So then if we have this correlations between V and R, we set to 0. We have this correlation matrix. We have the following Cholesky decomposition. So you see that it's only here, this part is very straightforward. Because this corresponds, of course, to the ordering of the variables. So first variable is R, second is V, and the third one is X. When you order those processes, always try to order it according to the simplest to the most complicated. So interest rate is the one, because those two are independent. So it doesn't matter whether variance is first or interest rate is first. And x, which will depend on both of them, we would like to keep as the last one in the Cholesky decomposition. Then that will not impact our simulation from the variance and also from error. Also, another thing is that if you perform this Cholesky decomposition, this is the process for xt, you end up with this square root of 1 minus correlation xr minus correlation xv. Often the question is, what if this correlation is not positive? Then it means that this correlation matrix that we have here is not positive definite. If it's not positive definite, essentially this means we cannot really perform simulation. So then there are also numerical techniques how to deal with a matrix which is not positive definite and you would like to force it to be positive definite. So then if this is not positive definite, then indeed you cannot do anything about it. You can think of some mapping on a matrix which is the closest positive definite, and there are some numerical techniques how to handle it. But then essentially that means that your correlations that you have estimated, they're not properly estimated. That's typically the signal, and you cannot really fix it immediately. You have to really think carefully how to adjust your correlations that this condition will be satisfied. So this has to be, in the term under the square root, has to be positive. And later, if we look at this more generic discretization, it's not necessary on Euler, but in the integral form, this is the term what we have. So after this Cholesky decomposition, our xi plus 1 is equal to those three terms, actually four terms. And if we would evaluate, we will approximate this integral by value at time ti only, then that is equivalent with Euler discretization. And otherwise, we may do some numerical techniques how to evaluate this. And this would be also one of these elements, how we are going to evaluate this almost exact simulation for the Heston-Hull-White dynamics. So this is a rather generic form of how this discretization will work. There is a few steps, important steps that we will need to take care of. In essence, it will be based on an approach we have worked on in exact simulation of the Heston model, and that was covered in the course of computational finance. Now we extend that approach with additional process for the short rate. The most challenging element of simulating, of Monte Carlo simulation of the Heston model is the problem of the variance that may hit zero. And that's typically associated with the failure condition. The details on the simulation of the Heston model and exact simulation you will find in a computational finance course in the lecture 10. There is a lot of details that we are not going to repeat today. However, I will show you the most important steps. So the approach here, of course, because we are dealing with Hull-White interest rates, and Hull-White follows normal distribution, this means that the simulation of short rate is rather straightforward. Therefore, also the extension of the Heston model to stochastic interest rates, it does not really require too much effort. It is more a technicality of adding additional dimension. Of course, keep in mind that although Monte Carlo, it is very much straightforward. If we talk about the fast calibration to Europeans, then we have to derive the characteristic function, and we have to perform fast Fourier transformations in order to get those densities. So in general, Monte Carlo simulation allows you to straightforward application. You can always define multi dimensions of different differential equations, but at the end the question is, practical question from the business is, okay, you have very complicated and very realistic model. What about calibration? If you cannot calibrate your model, typically this means that this model is not going to be used. And of course, that's the biggest dilemma. But this is also, if you look at the literature about models, stochastic volatility models, and maybe high dimensions, you will see there is not so many models available, actually. There are indeed a few important ones, but always the problem with models is that the calibration is very essential. So this practicality aspect, it really stops developing further the model. So if you cannot derive the fast approximation for pricing of Europeans, either whether it's whether it is a Fourier transformation or, for example, some kind of perturbation technique, then the model is not going to be used. Okay, if we go back to our simulation, so here we are now extending, or we are taking special case of the hybrid simulation. We are choosing Heston-Hull-White. So those functions a, b, bx, bv, and br, we have to choose accordingly to the Heston-Hull-White model. And this is then our generic representation. Of course, the part which corresponds to the interest rate, it is not difficult because it's only integral over normal process. The difficult part is actually the most involved part, is the part which involves the integral from the stochastic variance. But there's this trick, so if we have this, this will be a term corresponding to this term. Maybe you remember that if we look at the solution of the discretization of the Heston-Hull-White or Heston model, we will find something like Vi plus 1 is equal to Vi, and then we have a plus, so mean reversion. Here we will have long-term mean minus V, and this will be point I. If we just do discretization, dt, let's do delta t here, delta t, and then we have a gamma, we have a square root. Actually, in this case, we can actually do the integral, so it will be t, let's, instead of I, we just do ti plus 1, and here we have a ti. Then here we have integral from ti to ti plus 1. The same, of course, will be here, this integral delta t. And here we have a square root of vt dw vt. So in this term, actually, once we look at this representation and we choose those special cases for the variance process, this will be a square root of v, and this term would correspond to this term here. So this means that if we take vti plus 1 and this to the other side, also this term to the other side, then we know expression for this integral. And that's basically the whole trick about almost exact simulation of the Heston model, and also in our case, once we talk about almost exact simulation of a Heston-Hull-White. So let me maybe, to make it clear, I will rewrite here, so it will be v ti plus 1 is equal to v ti. To make it this really clear, plus we have integral ti plus 1 kappa v bar minus v t dt, and then we have this gamma integral ti plus 1 square root of vt, we have a dw vt. So now this will be corresponding, this integral is corresponding to this term here. So we can take all those elements on the left-hand side, and then basically we have a nice representation for this rather complicated integral, expressed in terms of samples that, or variables that we know at every point. Because this vti plus 1 and vti, we know that those are just non-central high-square distributions. So then we can really fit it to the representation of this integral. This will be also clear in this slide. So this is exactly what we did here. We did this representation, and of course, we still end up with, so if we substitute here, you see we have a dependence on dt, and this is what we see here. Of course, this kappa part and v bar can be taken outside of the integral because it is just an integral over time. So then we have this nice representation. And of course, here we can also do some approximation, because the difficult part is that here we are integrating with respect to time. So it's a z, it indicates time. So this can be also approximated by either trapezoidal integration or just evaluation at time ti, so at the initial point. But the most, let's say, the most fundamental part is not how we handle this, let's say, integrals with respect to time, but those integrals with respect to Brownian motion. And then, so this part, which is essentially taken from the almost exact simulation of the Heston model, if we plug it in here, essentially everything nicely collapses to this case with the extra dimensionality that we have for short rates. And this is what is here. So now a little bit of collecting of all the terms. So we see here we have a one integral of a variance with respect to time, this also integral of interest rate with respect to time, and then we have those corresponding terms which we can simply sample from the, this is non-central high squared. In next slide, I will show you how to get samples of this. But of course, details on this you will also find in the course of computational finance. And then we have some constant coefficients, those K0s, K1s, K2, K3. Those are expressed in model parameters. So I'm not going to show you how this derivation is done. You can either find in the course or in the book. And then for the remaining, we have still two integrals. Those are independent Brownian motions. So those two integrals we can simply approximate by evaluating Euler discretization. This is also mentioned at this point. So then we have a square root of VTI. So you see here, and then we have the same factor here of coefficient K3, and then here you also have correlation rho XR. So this is essentially the whole idea of this almost exact simulation, is to concentrate on the variance process, because that's the key process which determines, actually this is the most significant or most important process if we talk about accuracy. And of course interest rates are also important, especially if we talked about extremely long-term simulations. However, here the idea of the almost exact simulation is that we don't do very many small time steps, but our simulation would be requiring few time steps simulations, so large time steps. It doesn't mean that we just do a year or 2 or 5 years so large time steps, but for example, instead of having a daily time steps, we could do it, for example, monthly. And then those approximations that I have just discussed, those will be satisfactory to achieve that goal. So remember, if we talk about almost exact simulation, we talk about, because it's almost, we are not talking about explicit about extremely large time steps, but we are talking about moderate time steps sizes. And of course, if we compare that to Euler discretizations, that obviously would be very beneficial. Details on those discretizations, how big steps you can make, again refer to the computational finance course. And here, then we can also simplify even further this representation. So we will have a sampling from two independent standard normals, and then we still rely on this stochasticity here and here, and those will be samples from the non-central high square. So actually this will be non-central high square, so to be some degrees of freedom d and non-centrality, and then vi plus 1 is actually, this is not marginal distribution, it is distribution. To write it properly, it will be a conditional on realizations of I. So this is important step 2. And of course for the discretization, because here we still will have an dependence on Ri, so this is the process for the short rate, and here we will just follow the Euler discretization in this case. Of course, we can also do a large time steps in this for the Hull-White simulation, but when we have to take care of the Brownian motion that is properly represented and correlated with other Brownian motions. So then the simplest here would be just to do Euler discretization. Actually, for practical purposes, it is typically good enough. To summarize how this procedure for simulating Heston-Hull-White would look like, you see now it is important also how we have defined the order of simulation. So first we sample the variance process. We know the variance is independent of interest rates, so those actually doesn't matter which one is first, which one is second, but we make sure that sampling from process X is the last one. So first we do sampling from a variance process, so CIR at time ti plus 1, and here you see it will depend also on this, here it will be, the important one is a kappa bar, and kappa bar also depends on previous realization in the previous time step. So you see this dependence, it's a conditional on the previous realizations, on the previous time steps. So keep in mind that this sampling here, you have to use a whole vector of samples for VI, and that is used as the parameter. Once we have a VI plus 1, we also have, of course, VI, then we go sampling for the short rate or I plus 1, then we just do Euler discretization, and then we collect those VI plus 1s and also VIs, RI plus 1s, and then we put together to simulation of a process XI plus 1. As I have mentioned, we can do much more sophisticated discretizations, especially if we talk about short rate model, to make this large time step. So here we have a large time steps for the variance. We cannot really have a very large time steps for interest rates, but this is also you can extend it to make exact simulations or large time step simulations for the process Ri+1, and this will be also your homework, one of the assignments for today's class. Here, those coefficients, those are just a constant, so there is nothing really special about it. So you see, it's simulation of a Heston-Hull-White. Once you figure it out, what is the order, what the principles are, which process is the most important, where to use this almost exact simulation trick that we just relate the integral of the variance with the realizations at time ti+1 and ti, then if you put everything together, essentially we have 3 lines of coding, and then we simulate this 3-dimensional process, and this allows us to perform large time steps compared to Euler discretization. Now it's time to collect the techniques we have learned in today's lecture and put them together and compare to each other. First of all, we will consider the Heston-Hull-White model, so the model we have discussed in quite some detail. And here in this experiment, the objective is to compare Euler discretization, almost exact simulation, the one we have just discussed in the lecture, and then we compare those against the cost methods where we have used the approximation of the instantaneous covariance matrix, where we have mapped the non-linear terms, so the square roots of variance on its expectation. So this is the result that we see. These are the European option prices for a set of strikes. You see that the results are very good. In this experiment, I haven't done even a large number of Monte Carlo paths, and then the results will be more satisfactory. Let's take a look at the code, see how the simulation is performed. So here, let's start from the main function here. So we have some configuration for the full-white model. We have 15 years, so our maturity is 15 years, so it's a long maturity option. We have specification of the strike. So we take S0, which is 100, and then we look from the, this is the range of strikes we are interested in. These are the parameters for the Heston model, and also the correlation between stock and interest rates. Here is the discretization, or the Euler discretization for Heston-Hull-White. If we go to the definition, it is very straightforward. It's just a 3-dimensional discretization of the hybrid model. And here you see that actually what is important, because we do Euler discretization, we also have to make sure that the realizations for the variance are limited. They cannot exceed 0, so they cannot become negative. And then we make sure that this line here, that all the realizations are capped, are floored from 0. So then this is basically the Euler discretization. I also have performed here moment matching, this to make sure that we have this martingale condition satisfied. This is also very often applied in the industry. So if you have samples, you know theoretical expectation of those samples. In this way, you can ensure that the distribution is scaled so that the mean converges exactly or is exactly equal to the mean you expect to have. So this is the Euler part. We have also this is the part where we evaluate option prices for the paths. Then here we have almost exact simulation of the Heston-Hull-White model. So you see it is very much, it's maybe a bit not some, there are a few lines here of code, but we still simulate Brownian motions, and those are the K1, K0, 1, 2, and 3, and so on. And then we have this discretization for X. Here we have also discretization for R, and we also need to perform the variance sampling from the CIR. So you see, for example, here, this is exactly what I mentioned before, that VTI+1. Also, we need to calculate the sample. We have to use as an input the previous realizations on time step. And this sampling here is actually exact sampling. So we have exact sampling from the non-central high squared, but of course we don't have exact sampling from the integral of a path. So that's a different story, because of course we had this integral of a variance of a square root of v times Brownian motion. So that's a different if we look at the sampling only from the non-central high-square distribution. So this is, you see, this is just implementation of what we have seen in the slides. And then the final part, we do Euler not the Euler discretization, but this is cost method for the Heston-Hull-White with the approximations. This will be here. We do the cost method for the approximations we have discussed in this lecture. So this formula here, this line here, we derive the approximation for the characteristic function. Let's take a look where it is. It should be somewhere here. So this is the characteristic functions for the Heston-Hull-White, assuming non-zero correlation between interest rates and stocks. So all those functions, individual functions, are here, and then we have also the square roots that we have approximated. So if we run this, of course, it will take a bit. It is not super fast because we still rely on Euler discretization. So obviously that is a little bit time consuming. Then in this way, here we confirm that results are very good. We have how many samples? We have 10,000 samples. So of course, this is also not very large number of Monte Carlo paths. This normally should be a range of 100,000, but or even more, especially if we talk about now we are talking about comparing different methods. So then obviously it is very important to have a large number of samples to really remove the noise which comes from Monte Carlo and concentrate on the approximations we have implemented or we have imposed on the model in order to get the characteristic function. And also for almost exact simulation, we have performed also some discretizations. So typically we would use for, let's say, comparison reasons, very, very large number of Monte Carlo paths. And then, of course, in practice, we can reduce that. But of course, before you have to make proper analysis, what is proper number of paths or satisfactory or the lowest number of paths such that the error is in an acceptable range. So that's the ultimate goal. Now is the time to summarize what we have learned in today's class. We've concentrated today on hybrid models, and I have shown you rather simple models like Black-Scholes-Hull-White, and later we moved to more advanced models like Scholes-Hull-White and Heston-Hull-White. Those two hybrids, actually, they were different with respect to Black-Scholes because they allowed for stochastic volatility. Of course, ultimately in this course, we would like to perform simulation of our XVA, and then this impact of a smile or skew in the XVA calculations may be significant. However, often in practice, people would rather stick to simplistic models, like, for example, Black-Scholes-Hull-White, and they concentrate more on those models with the extensions of, for example, time-dependent parameters. So that's practice, that's industrial practice. Let's take a look exactly what we have covered here. So the Black-Scholes-Hull-White, we discussed also the concept of implied volatilities in the context of stochastic interest rates. So how to calculate Black-Scholes implied volatility if we have stochastic interest rates. And then we move to this extension of those hybrid models with stochastic volatility, or let's say we extended stochastic volatility with stochastic interest rates. And then I gave you a little bit of motivation of using hybrid models, but not only for, let's say, in the context of XVA or VAR calculations, but also in terms of a pricing of hybrid payoff. This hybrid payoff is the one which involves multiple asset classes in one payoff evaluation. And then quite some attention we spent on simulating Heston-Hull-White model. So I gave you some hints on how to perform fast Monte Carlo simulation or simulation that allows you for large time steps in your pricing or your simulations, and also show you how to perform approximation of the model such that you can perform fast Fourier transformation. Thus, you can use this model for fast calibration of your model to the market data. And now is the time to summarize that we are doing and homework. I have prepared two exercises. The first exercise is it's not Heston-Hull-White, but here we actually we will have a little bit more advanced model. We have a Heston CIR. We have discussed that CIR model is not maybe ideal these days because interest rates are negative. But let's forget about it. Of course, we could fix that negativity by, for example, shifting the short rate, but let's don't do that. And here we would like to perform approximations, so we will end up exactly the same problem we had for Heston-Hull-White, that we have those square roots, which are not really nice to deal with. Objective is to find those expectations of these two. Actually, you will see those processes are very much alike, and derive the characteristic function. Of course, ideally, you would like to also compare your Fourier transformation to Monte Carlo simulation. So that I leave it to you, whether you would like to do that. Of course, you can still perform some sanity checks, even for your Fourier transformation. And for those, what kind of sanity checks, I recommend to revisit the computational finance course. The second exercise is to develop a Monte Carlo simulation, but not maybe Euler discretization, but more large time step simulation for Schobel-Zuchel-White model. So this is the one we also have discussed in this course. And here you need to develop Monte Carlo simulation, check the convergence, and derive the characteristic function. This characteristic function is rather involved, so I would recommend that you will derive the corresponding ODEs, those ordinary differential equations, Riccati type of equations, and then that will be enough. But of course, the main objective here is to derive the fast Monte Carlo simulation, or Monte Carlo simulation, which allows you for large Monte Carlo steps, and then compare that, please, to Euler discretization. I hope you have enjoyed this course, and we will see each other next week.